Hi everyone and welcome. Thank you all for being here today. We're very excited to have with us two speakers today. Our first speaker is Dr. Jonathan Sauder, who is a mechatronics engineer at JPL and is a charter member in the Technology Infusion group, which seeks to bridge the TRL Valley of Death for innovating promising technology concepts. He focuses on developing unique and innovative mechanical systems, many of which are related to deployable antennas and sunshades. He is the mechanical engineering lead of the RainCube spacecraft and the principal investigator of the NIAC study Automaton Rover for extreme environments, as well as two deployable antenna research projects. He completed a PhD in mechanical engineering in 2013, focusing on how collaboration aids engineers in creating innovative designs. Our second speaker today is Evan Hilgemann, who is a mechanical engineer at JPL as well, and his job responsibilities range from developing novel technologies for space applications and matures flight system design. Evan was the lead mechanical engineer for a meter-scale deployable CubeSat antenna and currently contributes to other large deployable systems, including the surface water and ocean topography satellite and Starshade. His technology interests lie primarily in the areas of large deployable structures, rapid prototyping, and robotics. He earned an MS degree in aerospace engineering from the University of Michigan and a BS degree in mechanical engineering from the University of Nebraska-Lincoln. So with that, I'll hand it over to our speakers. Please welcome them.
Excellent. Thank you, and thank you for having us here today. So, we as humans have always looked up at the stars with wonder and amazement. And we've wondered, are we alone out there? What else is out there? What else is up in the stars? And if you would have been here 2,000 years ago, another big question that would have been on your mind is, why do some of the stars wander, tracing these intricate patterns across the sky? Now, the ancient Greeks, in order to try and understand more about the astronomy around them and the celestial bodies, developed the Antikythera mechanism. This is a mechanical computer from 200 BC where you would crank in the date and it would output the position of the sun, the moon, and possibly even those wandering stars, or what we know today as planets. However, what's truly incredible about the Antikythera mechanism and this device is that not only was it a mechanical marvel at the time, but it may even provide the inspiration for exploring one of those planets today, Venus. With a temperature that'll melt lead, a pressure that'll crush the hull of a nuclear submarine, and a sulfuric acid atmosphere, it's one of the most extreme environments within our solar system. To put a little bit of context about Venus's environment, if that blue temperature bar is Earth, red is the average surface temperature on Venus. If you notice, that's from absolute zero at negative 273 C, because if I would go from 0 degrees Celsius, Earth's average temperature would barely be a blip compared to Venus's temperature. To put 462 degrees Celsius in a little bit of context, military spec electronics, the most robust off-the-shelf components that you can buy, are only rated to 125 Celsius. Paper spontaneously combusts at 233 degrees Celsius. And lead and solder turn to liquid at 300 degrees Celsius. The pressure on Venus is extreme as well, 98 times that of Earth. If you were to take a gallon of air here on Earth, it would compress to just 1.5 shot glasses on Venus. Despite these challenges, in the 1970s and 80s, we, and mostly the Soviet Union, successfully landed about a half dozen landers on the surface of Venus. And this is actually a picture from one of them, the Soviet Venera 13. The only issue is that it only communicated for 2 hours and 6 minutes before it stopped operating and succumbed to the environment. The problem? The electrical systems on board just couldn't take the heat. Fast forward to today, and modern flagship mission proposals, or even other mission proposals, don't do much better, only looking at 24-hour time periods. However, if we were able to build a rover that was mechanical in nature, drawing from the Antikythera mechanism, that was built out of steels, titaniums, and high temperature alloys, and we would of course have to account for the coefficient of thermal expansion, we could design something that could operate on the surface of Venus for weeks, if not months, rather than just hours, greatly increasing the lifetime of the mission. So hence came the idea, the Automaton Rover for extreme environments, inspired by the steampunk, I guess, sci-fi trend, or similar to that. It's a fully mechanical rover that could roam the surface of Venus, place instruments, be powered by Venus's wind, and then signal the science information to an overhead orbiter using a radar target through a mechanical system. So an automaton is a mechanical robot. And these automatons actually started their development in the 1600s, which we'll get into in just a minute. So my name is Jonathan Sauder. I'm the principal investigator on this project. Here with me today is Co-I Evan Hilgemann. Other co-Is on this project are Jesse Kawada, Katie Stack, Aaron Parness, and Michael Johnson, all from JPL. And this is a project that's in phase 2 funding from NIAC, NASA Innovative Advanced Concepts. If you aren't familiar with the NIAC program, NIAC is the wing of NASA that funds visionary advanced concepts, things that wouldn't necessarily have another way of getting funded, and that are probably a decade or so from implementation. They also fund concepts that are a little bit more on the high-risk end of things, ideas that really wouldn't have another approach for moving forward. So hence, an automaton rover, a mechanical rover, is a perfect fit for a NIAC study. But first of all, why do we want to have an automaton or a mechanical robot on Venus? Or why do we want to survive on Venus for a long period of time? Well, there's a lot of data that these short-term missions that last for only hours don't get at. And we need to understand sort of why is Venus the way it is, what makes it different than Earth. And to get at this, we can start to try to understand what are diurnal weather fluctuations, which you need to be there for a long time. Is there seismic activity on Venus, and to what extent? What is the makeup of the interior of the planet? And those are all things that can give us clues as to why Venus has evolved to become such a different planet from Earth. Finally, how does the geology vary across Venus, and what is it like on the various regions? So in coming up with this concept, we're actually inspired by a number of things. And if you read the abstract, it mentions 16th century technology. And that's because automata really started their development in the 15 and 1600s. This right here is an automaton called the Rider by Swiss clockmaker Jacques Droz. It's a fully mechanical robot from about 1650. Look at the detail with which the hands, the eyes, and the head move. And this is an incredible mechanism that is all controlled by a series of cams in the back of the boy here. These cams interact with levers, and each lever, one lever moves the arms, another lever moves the head, another one moves the eyes. But then what determines which cams are selected to determine which levers move are these keys in the back. And you can see each key is related to a letter. So as this lever hits different keys, it'll of course result in writing a different letter on the piece of paper. But what's really incredible about this automaton is that you can take those letters out, reprogram them in any sequence that you want, and have it write any sentence that would be possible. So we thought, what happens if instead of just writing a phrase, if instead we would take a mechanical robot and program it to instead do science instead of that? We could build something incredible that could operate for long periods of time. Another thing that was really inspiring to us was Theo Janssen's strandbeests. Now these are incredible wind-powered creatures that roam the beaches of the Netherlands. And while they look amazing, perhaps what's even more amazing is that they have very simple mechanisms on them that can sense as they're walking into the ocean or as they're walking into soft sand, and they'll actually reverse direction and go the other way, such that they have a simple obstacle avoidance system. And this provides an inspiration for what we would do with an automaton rover. So I'm going to start off with showing you sort of a systems diagram that we came up with for this automaton rover in phase 1. And this is just sort of the starting point for telling our story. And we'll go through and talk about different developments and what we discovered as we refined a rover concept. So you can see we initially start off with a wind turbine. We get wind power that comes in. We're looking at storing it in a spring. We have a mechanical computer at the core inside the body here, which does all the processing, kept in track in parallel with a mechanical clock to help us navigate the surface of Venus. We'd have a series of mechanical instruments on board, which I'll talk about specifically later. And then we'd have legs, which are directly connected to the power system, as well as a mechanical computer, which would direct it where to go. So our approaches for getting power on Venus, our reason for using wind power, is we started to investigate what are the different power sources on Venus. And this chart here shows sort of the different types of wind turbines you could have, each of course with different amounts of complexity and number of deployments. So this one here requires 1 deployment, this right here requires 2 deployments, and the Savonius does not require any deployments to fit inside the rover space. And we sort of looked at what the power we could generate in that, and then what that power density was as well, given an average Venus wind speed of about 0.6 meters per second, which is pretty slow. The wind speed on Venus varies between 0.3 and 1.3 meters per second, but it's very dense, which gives you, which does help slightly increase the power, and makes up for it a little bit better than what you would get with those speeds here on Earth. We also compared this to RTGs, radioisotope thermoelectric generators, which a lot of spacecraft use. You can notice that when RTG would be relatively high power density in watts per kilogram. But the problem with RTGs is they're very expensive to develop. And no one's really developed an RTG for a Venus mission. So you'd have a very high cost development to build one for Venus, and you wouldn't quite have the justification that you have with the multi-mission RTGs that you can use in other cases. We also looked at solar power on Venus, which is another interesting option because solar panels will actually operate at 462 degrees Celsius, and there's been some research at JPL that has shown that they work. The problem is, first of all, you need a very large area of solar panels because the sunlight that gets down through the surface of Venus is very low, about 32 watts per meter squared, so a fraction of that of what you would have available to a regular spacecraft. The other issue is that Venus rotates very slowly. Its day is about 60 days long. What that means is that you have a 60-day night as well. That would be time when the solar panels would not work and the rover would have to go through power cycles, which of course is undesirable. We also looked at how you would store the energy once you generated it on Venus. So I should note then wind power seems to be the most practical approach for Venus overall. And then once you have that energy, you need to store it. So we looked and compared it to batteries, to various mechanical approaches to storing energy, compressed air, flywheels, springs, and using gravity with a tower. And you can see, of course, why most spacecraft use batteries, because they're very high watt-hour per kilogram energy density. The problem is that while theoretically batteries can work at 462 degrees Celsius, getting it to work in actuality is a bigger challenge, and no one's actually demonstrated them, rechargeable batteries at least, working at these high temperatures. So what we're leaning towards is the metal or composite springs, because those are likely going to be the most robust. We also looked at flywheels and compressed air. Flywheels, of course, have the issue that, in general, they work in a vacuum with Venus's high-density atmosphere. You get a lot of drag on them. And compressed atmosphere, if you compress air to store energy, you, of course, then also have to worry about leaks. One of the biggest questions that we got when we were initially coming up with this concept is, how do you get the data off a mechanical rover from the surface to an orbiter off the planet? Right? It seems to be a very big challenge. And if you would have read our initial Phase 1 proposal, we proposed using records and balloons. So we would inscribe data on metal records, which could operate at Venus temperatures, launch them via balloons into the high atmosphere. One of the interesting things about the atmosphere, once you get about to 50 kilometers or so on Venus, is you can actually get above the sulfuric acid cloud layer. And at that altitude, too, the pressure and temperature is very similar to Earth. You're about 120 degrees Fahrenheit or so. So it's hot, but not too bad. So you could operate a solar-powered drone at those high altitudes. But of course, this is a bit of a Rube Goldberg, and it'd be hard to find a balloon, especially in Venus's high winds, floating around the entire planetary surface. So maybe we had to look at another option. So we started looking at vacuum tube transmitters. Now, you're going to say, but wait a second, Jonathan, I thought you said electricity doesn't work on Venus. Electricity actually works fine on Venus. The problem is modern transistors do not work on Venus, and the materials they're made out of do not work. So we looked at using vacuum tube transmitters, which vacuum tubes actually work great at high temperatures. The problem with this, though, comes in the pressure, and it becomes very challenging to maintain a vacuum at Venus pressures. So finally, we came up with this idea of a radar target, or a radar retroreflector. Now, what a radar target would be is it's similar to a reflector on a road sign or a bicycle, where when your headlights hit it from a car, it would shine back very, very brightly, and that light would bounce back and create a very bright spot. You can also think of it a little bit, of course, if you're shining a light down on Venus, it couldn't get through the cloud layer, so you have to use radio frequency energy, or roughly X-band frequencies, instead of light. Now, if you are, another way to think about this is that it's sort of also the opposite of stealth technology, where a stealth plane is designed specifically with shapes to try and deflect a radar signal as much as possible and make it as dull as possible. In this case, we have a very specific design, in this case a corner cube, to shine back that radar as bright as possible. Now, a bright spot on the surface of Venus isn't enough to communicate data, but you put a shutter over that light, and now you start to get a flash. And as that flashes, you can start to communicate information, much like semaphore used in World War II to communicate between battleships. So we put this out and started looking at what our data rates were. And as you may imagine, a radar target compared to a vacuum tube radio or a traditional radio has a very low bit rate. So you end up sending very small amounts of data back from the surface of Venus. But one of the things that's important, though, is that doing some preliminary radio frequency calculation with some of the radar folks at JPL, we showed that the trade closed and that you could actually communicate with a fully mechanical system from Venus to an overhead orbiter. Now, one thing you'll notice here is on the right-hand side, I have something that mentions high temperature transceiver. You may be wondering, wait a second, I thought that modern transistors don't work at Venus temperatures. Well, there are silicon carbide and gallium nitride electronics which do operate at Venus temperatures. The problem with these is their level of integration is about 100 to 1,000 transistors on a chip, which is equivalent to a 1960s calculator. Basically today is the rough equivalent to a solar-powered calculator, is the complexity of what they can do. Also, there are some severe limitations on these current silicon carbide and gallium nitride electronics, and to my knowledge as of yet, no one's developed a transmitter that can oscillate at the right frequency to get through Venus's ionosphere. So there is no high-temperature radio which will work at Venus temperatures, at least yet. Therefore, we need the radar target to provide a way of getting data from the rover to an overhead orbiter. But this brings up our first design principle that we learned in our phase 1 study, is that using mechanisms to enable and electronics to enhance. So one of the things we want to think about is finding a way that we can do this mission entirely with mechanisms such that we don't have to wait on future research in high temperature electronics, which may or may not pan out, and find a way that shows we can accomplish a Venus mission with the mechanical technology that we have today, rather than waiting on developments in high temperature electronics in the future. But of course, if in 5 or 10 years that high temperature radio would become available, we would use that to increase our data rates and to improve our overall capabilities. To sort of give you an idea of what that radar target would look like, this right here shows a radar map of Venus. And if we were to zoom in on this radar map and get to 1 pixel right there, you can see a white spot flashing on and off. And that would sort of be what the orbiting radar would be looking at and seeing transmitted from the surface of Venus, is 1 pixel getting very bright as that radar shutter opens and closes, and through that be able to communicate data. All right, next I'm going to turn it over to Evan Hilgemann to get into mechanical computing. But while he's coming up, just a quick video to give a little bit of historical perspective on it as well.
This is truly one of science's great achievements. With it, complex problems of synchronized machinery, electrical systems, trajectories of particles and large masses, and the like, now can be quickly solved. For example, giant rockets, which will speed to the moon and our sister planets, are now being perfected. Limitless as space are the dreams of science. Aided by the mechanical brain, they may soon become everyday reality.
All right, so as you guys can see, mechanical computing is, of course, not a brand new technology. These concepts really became mature during World War II and just after, when this video came out. And at the time they were developed, this sort of technology is what people thought might enable us to explore space in the future. This is what's going to get men in space into the moon. We, of course, know today that it didn't quite work out that way with the invention of the transistor. However, this is still really a viable method for us to use to help us explore space even today when we do have high-performance electronics and other areas. And before we get into that, I'm going to give a little bit more of a historical perspective here and go over a couple of examples of mechanical computers. And really one of the simplest, oldest mechanical computers that we have available to us is the mechanical clock. Clocks have been around for a long time. This is the Salisbury Cathedral clock. It's been continuously operating for centuries now. And one particularly good example that I like regarding a clock that helped solve science problems of its day is what's known as the H5 pocket watch. This watch was developed by John Harrison in the 1770s, and it won what was known as the Longitude Prize. This was a big effort, an award offered for the first person who could develop a way to successfully determine a ship's longitude at sea. Most people focused on astronomical methods to do that, but John Harrison had a different idea. He thought he could make a timepiece accurate enough to be able to determine longitude at sea, and indeed that's what he did, and he invented this, a pocket watch that's accurate enough to tell longitude. I talk about these both because we're going to have to keep time on our rover, and also we're going to have to employ similar problem-solving strategies, come up with unique mechanical solutions to solve engineering problems and provide a science return on the mission. Some other well-known mechanical computers came about in the mid to late 1800s. The image on your left here is a model of the Babbage engine. Also, other iterations were known as the difference engine. This was invented by Charles Babbage. He made designs on paper. He never actually built them, but they were replicated later on. Anyway, this is the first computer that's reprogrammable in the modern sense. It takes inputs, gives you outputs, it has memory banks. It even has a central processor, much like modern computers today, but 100 years before anything similar to our concept of a computer was invented. And the other thing to keep in mind is mechanical computers weren't these very rare things at the turn of the 20th century. This image on the right is an arithmometer. If you were an engineer 100 years ago, you probably had one of these on your desk, and it was a mechanical computer. It could add, subtract, multiply, divide, take care of those functions for you. So mechanical computers, were commonplace for a long period of time. As I mentioned before, the mechanical computer had its zenith around World War II. So there were fire control computers developed to go on airplanes, go on ships, that could take anywhere from a couple dozen different inputs, do calculations, and figure out where to point your guns. This was, of course, immensely valuable to the war effort, and some concepts here that we played off of to develop our system. The next thing I want to talk about here is different types of computing. So we went through some historical examples, and I want you to understand the different, aspects of those computers. First off, whenever I say computing, at least, I think of binary computing. Ones and zeros, OR gates, NOR gates, ANDs, all of that. And most of us probably know if you put those together in the right way, you can make circuits that add, do other things. And that's what modern computers are based off of. You can replicate every component of that, at least down to those individual logic gates with mechanical components. There are mechanical OR gates, AND gates, whatever you want. And this is actually where we started at with our original proposal, is we were going to try and replicate a modern computer using mechanisms, even going down to the MEMS level to try and enable this and at least get some of the functionality of a computer. But what we did find is this really just isn't a practical method compared to other computing methods available to us to help solve our problems. So we'll get into some of that in another couple of slides. We can also look at digital computing. So binary is just a specific type of a digital computer. It just happens to be base 2, but digital computers can also be base 10 or base 3, base 12, whatever you want. This is a cutaway of an anemometer, which was probably base 10. The digital basically just refers to that you don't have a continuous spectrum of outputs. You have discrete points, and depending on which discrete points you end up with, that gives you a solution. And that's an advantage for a digital computer, right? There's no ambiguity about what your solution says. They can also be more easily reprogrammable than analog computers, which we're going to talk about in a second here. But what we found is they tended to be larger, a bit clunkier than analog counterparts. So the last type then that I'm going to talk about are analog computers. We actually like these quite a bit because they were fairly well developed with the war effort. Here you can see a Navy training video. And with simple mechanical modules, you're able to accomplish different goals. So here's a mechanical addition machine. It's just a bevel gear differential. It's one single mechanism that's doing your mathematical function for you. We have a multiplier here, so that's just a couple of sliders and a pin. You're able to do mathematical operations with it. And let's see here. And my personal favorite here is the mechanical integrator. So, multiplication, addition, you can kind of see how that would work. But here we have a way to even integrate a function entirely mechanically. So we're looking at using some of these mechanisms in our system to enable greater functionality of the rover. And because this is Caltech, we're actually going to do one better. We have an actual mechanical computer here that Alan Bryce brought in for us. It appears to be yeah, and you guys will have a chance to look at this after the talk too, so it's all right. But this is a computer probably out of a fire control computer. That's a sine and cosine calculator. So you're welcome to come up after the talk and take a closer look at this if you would like. Okay, and we have another, type of computer, if you will, type of analog computer called a bar linkage computer. So say if you need to solve an equation like the range equation, again, figure out where you want to point your gun at. This problem comes up a lot in these analog computers. But you have a rather complex equation to solve. But it turns out with just two 4-bar linkages put back to back to each other, you're able to solve this equation. Again, it's just 2 inputs, 1 output, and that's able to increase the functionality of your instrument. So now I'm going to come to our second design principle here that we came across, that we want to utilize these sorts of mechanisms to reduce requirements on our electronics. So we probably aren't going to fully replace our electronic systems. There are going to be areas where they make sense to include, but as Jonathan alluded to, their capability is fairly limited compared to what we think of as being a modern computer. We can't do as much with them. So what we want to do is utilize these sorts of mechanisms, take computing load off of whatever electronics we have, and end up with a system that is more capable overall in the end. Now there's some questions about how we actually architect our system to do that. So I want to go into that a little bit too. So I'm going to talk a bit about robotic architecture models. The typical robotic architecture is what's called the sense, plan, act model. This is when you have some centralized core brain, something that's highly complex, that takes in all of your sensor inputs, models it, figures out what's going on, sends outputs to your actuators and anything else in the system. It's the one decision point in your system that's doing the controlling. What we want to do is look at more of a distributed model. So instead of having that one complex core, you have a bunch of distributed nodes, if you will, each of them completing some sort of simple behavior. When you put all those behaviors together, you end up with a system that can complete complex behaviors. So it's a way to break down the problem into much more manageable systems, and then by integrating that system in a clever way, you're again able to perform complex behaviors without going back to having to create a central brain that's very powerful. So this is now our third design principle here, is that we want to use these distributed simple mechanics to lead to more of an evolved emergent behavior as opposed to having one node or one central brain that's very powerful. And people have looked into these robotic models before. We've leaned heavily on the behavior-based robotics methods. These were largely developed in the mid-1980s into the early 1990s. In particular, we relied on work by Rodney Brooks. He developed something called the subsumption architecture that basically decomposed a robot's goal into different layers. And then even from there down into smaller layers or smaller components to do more or less what I've been saying. Have a robot that relies on very simple rules to accomplish complex behavior. So Rodney Brooks developed some of the first robots that could accurately explore their world, avoid obstacles and whatnot, and that's actually very similar to what we need to do on Venus. We need to explore our world, we need to avoid obstacles, keep the rover safe, and accomplish science goals while we're doing that. And to that effect, we have looked at a simple case study to kind of try and start proving out what our system might look like. This is your straight-up obstacle avoidance study. You have something in the way of your rover has to sense it, move around it, continue on its path. So we put together a couple of conceptual, mechanisms here, how this might look. We decomposed it into 3 different three different behaviors, if you will. One doing energy management, just figuring out how much power you've collected and when it's safe to actually move for the rover to move. Your actual obstacle avoidance, which is detecting if you hit anything and then moving the rover out of the way. Also something that'll resume your original path. Now what we want to do in the next 3 to 6 months now is take this and actually, instead of having it just be something on a piece of paper, build a system that can mechanically rove around on the floor of it in a cluttered environment and avoid obstacles. And we're going to be leaning on some of the other references that I talked about, Rodney Brooks and some of his work, and actually take the state machines that they used, fill it in with mechanical systems, and put those together so we can achieve our end goal. And with that, I'm going to hand it back to Jonathan.
Thanks, Evan. So, as we started to develop this concept further in our phase 1 study, which was our initial study, we had at JPL what's called an A-team study, or an architecture study, where we bring a lot of engineers and subject matter experts into the room to discuss the mission concept and develop the mission concept in more detail. And in that A-team study, actually, we're fortunate enough to have Theo Janssen, the creator of the Strand Beast, come in as an expert on automatons. And he volunteered his time to talk with us and help give us some ideas on executing automatons in Venus. And this A-team study really sort of led to a different architecture evolving in our concept. We moved from something that was a very intricate rover. One of the things that Theo mentioned when he first saw this was that, the legs on that look beautiful, and it's probably part of the reason your phase 1 proposal was selected and you won, because of the imagery that creates. But from my experience on the beach of the Netherlands, the legs are even unstable just on sand dunes. You need to be thinking about something that's going to be a more robust system. And we sort of started to realize that was something that was across this rover entirely, is that it was a fairly intricate rover with components trying to either maximize the energy collected from wind power or placing instruments in different locations. And we needed to look at something that was going to be built much more robustly, actually, much more like a tank. In fact, it was inspired by World War I tanks, which were specifically designed to drive across trenches and through shell craters and climb steep grades. So you'll notice that in this design too, we've moved to where the tracks wrap all the way around the outside perimeter of it. This means we can operate independently of orientation. So despite not only being able to climb large obstacles, we can roll over and keep operating. So we can operate regardless of what orientation. And this actually brings another key design principle, the fourth key design principle we learned in developing this mechanical rover for Venus, which is to use robustness and resilience to reduce complexity, right? So why not worry about having an extremely complex system to avoid the smallest obstacles, but instead make it so you can drive over as many obstacles as you can and therefore reduce the complexity required on the system. Now, one of the things we were looking into too is how we could accomplish science with a fully mechanical rover. And there's a lot of things we can measure: wind speed, temperature, pressure, seismic events. You can measure wind speed, of course, with how quickly the wind turbine's rotating. Temperature, if any of you have taken apart an old thermostat, you would see inside it there's a coil spring that basically, as the temperature heats up or cools down, the coefficient of thermal expansion on that spring causes it to expand or contract and causes the thermostat to turn on and off as this end piece moves and either hits a switch or disengages from a switch. We can measure pressure by a changing volume of a control volume. We can measure seismic events, at least crudely, with the cantilevered mass. We can also measure chemical composition if we were to have various samples that were loaded on either end being pulled apart and then be exposed to the atmosphere. We can measure the amount of time that it would take for that sample to degrade, and when it broke, we would know what the chemical composition was of the atmosphere. So we could do a lot of things very basically. But as we started to look into the high temperature electronics that existed in the silicon carbide and gallium nitride electronics, a lot of these sensors have actually already been developed for use in jet turbines and can be accomplished with the silicon carbide and gallium nitride electronics. So we realized that with the rover architecture that we were looking at, we probably needed to look at definitely doing the instruments from a high temperature electronic perspective, and that would allow us to get higher resolution data, which led to our fifth key design principle that we've learned in developing the Automaton Rover concept, which is that a hybrid rover architecture maximizes performance. You can see here, it's similar in our previous design that we still have the wind turbine coming in, storing the energy in a spring. But then, of course, we have the distributed mechanisms to do control of the rover at various points. So various obstacle avoidance sensors that would be directly connected to the tracks and wheels, telling us when to reverse or go forward to avoid obstacles. We have our signaling system here, and then we would have silicon carbide and gallium nitride instruments that would measure the Venus environment and detect chemical compositions and different things like that. You'll also notice here that we're also including solar panels on the rover. Now, and these right here would of course provide supplemental energy to run more instruments during the day. So during the Venus day, we can accomplish a lot more science. During the night, when we have just wind energy, we'd have to cut down on the amount of science that we can do, but we can use that to help increase the amount of science that we can accomplish on the Venus surface. So this shows an overall sort of 3-view drawing of our concept, as well as with an astronaut scale to give you an idea what the size of that is. You can see most of it is wind turbine here in the center, so most of it is empty space. The total mass of our concept comes down to about 1,100 kilograms, which fits within sort of the landing capabilities proposed in some of the decadal surveys for short duration landers. So we wanted to fit within what could work from some of the decadal survey reference missions. You can see on the top we have radar targets here. There's also, of course, going to be radar targets on the bottom, so when we flip over, we can still communicate with an overhead orbiter. And there's basically just these spinning disks here, which will shutter the corner cubes here, flashing them on and off. There's a couple other systems, though, of course, too, that we'd need to execute this concept. One is an EDL system, entry, descent, and landing system. And when you enter the Venus atmosphere, it's slightly different than when you're landing on Mars. The first couple sequences are fairly similar, where you have an aeroshell that comes in through the atmosphere at a high speed and is going to experience a lot of thermal loading. Then you'll open up a drogue chute. After that drogue chute, sometimes you're going to have a main parachute, sometimes you won't. But then the key difference occurs right in this phase here, where the rover would come down on a drag plate. Venus's atmosphere is so dense, once you get to a low enough speed, you can just have a big plate that slows you down and allows you to land on the surface of Venus. We'd also, of course, need an orbiting radar to go along with this, and we sort of baseline something that would be similar to the Veritas radar to communicate with our rover. One of the interesting things, though, is there's a lot of places, though, you can use a mechanical rover beyond Venus. So other places that we've looked at and seen applications for this rover beyond Venus are the Jovian moons. This is where you'd have a lot of radiation, which you're going to do a long duration mission will definitely have a potential issue with your memory and potentially other electrical systems on board. So using mechanisms on a long duration Jovian lander that would be in the radiation belts of Jupiter for years could be a very compelling case. Another would be gas giant probes. You go inside a gas giant to get very dense and very hot very quickly. So you could use a mechanical probe to explore gas giants. Also contamination control areas where there's a lot of contamination control sensitivity, like for example the streams of water that we've seen on Mars. And those would be a place that scientists would love to get a sample from. The problem is you can't clean electrical rovers clean enough to make sure that there's no bacteria that's going to get to those places and potentially start living there on Mars. So what we could do, though, is we could design a mechanical rover that can be very well sterilized and send it into those contamination control areas and work in tandem with an electrical rover. We could also use it to explore volcanoes here on Earth, as those are another high temperature environment where this application could be used. So our next steps in this study, well, we're currently at the beginning of our phase 2 work of this. We've completed our phase 1 work, and we have about 2 years of funding to continue to develop this concept more. We'll be building a couple of rough prototypes in this study. And after phase 2, while it'd be great to get directly proposed to a New Frontiers or Discovery mission, probably after some bridge funding, we also want to look at other opportunities beyond direct mission applications as well for infusing bits and pieces of this technology into spacecraft missions that could be enabling. And one of the interesting things is that the clocks we've been looking at, we've been looking at developing a clock for high temperatures. This is actually an example of a clock that we baked at 460 degrees Celsius. The first prototype failed miserably, as they usually do, but we're actively working on building another one. But building a clock for for operation at these high temperatures actually has use for other high temperature landed weather stations on Venus. So there's some people with the very simple gallium nitride and silicon carbide electrical components have been able to build some very simple ideas for a weather station on Venus. But the problem is these have a very limited lifetime because they only have a primary battery that's non-rechargeable. But you can really help extend the life if you would have a mechanical clock that could turn it on and off, such that it'd sort of wake up every day, make a measurement, and then get turned off until the clock comes back around to the next day. We've also been looking at concepts for airborne turbines to generate electricity on Venus that could be potentially suspended by a balloon. So that's another potential infusion path, is using what we're learning in designing wind turbines for Venus for applications to provide more power to long durations Venus missions. But finally, really what we want to do here is start changing the conversation, making people think that, you know, we don't have to wait for future developments in high temperature electronics to develop a rover for Venus. This is something that with mechanisms we can actually do today, and actually do this with technology that's already available to us, and change the conversation, because currently everything in the decadal survey, all the current Discovery New Frontier mission proposals, all focus on short duration landers which last less than 24 hours. We want to change that conversation and get people thinking you can do longer Venus missions if you're able to think about it a little bit creatively. And in fact, we can even do long duration rover missions. So in summary, to enable those long duration missions, some of the key takeaways that are the principles for executing this design is that first, mechanisms enable, while electronics help enhance and give us more value for our mission. We can utilize mechanisms to reduce the requirements on the electrical system to enable us to launch a lander with technologies that we have available today. We can also use distributed simple mechanisms to create an evolved emergent behavior which can adapt to the environment. And that we want to use robustness and resilience in our rover design to reduce overall complexity. Finally, we can use a hybrid rover architecture to maximize the performance. And this gets back to this theme sort of at number one again, mechanisms enabling and electronics enhance, where we use the mechanical systems to enable a rover with what's available to us today, and then use the electrical systems to help enhance the science that it's able to complete. So this is a very exciting concept, and well, it's exciting to think about being on Venus and being able to take long duration data from Venus. How does this relate to the average person's life? And why should the average person on the street care about getting data from Venus? And the reason for that is we can come back to sort of where we started. We still today look up at the stars with wonder. Wondering again, are we the only ones out there? Is the Earth the only place like it in the universe, or are there other Earth-like places out there? And if so, does life exist there? And one of the exciting things that we've discovered in the last decade is that nearly every star, at least statistically speaking, has a planet that orbits it, or we know these as exoplanets. And there are billions of Earth-sized exoplanets out in the solar system. So how do we go about determining, though, whether that Earth-sized exoplanet is something that can support life or not? One thing we can do is we can look at Earth and try to understand Earth and see, are there similarities between it and Earth? But another way we can do it is by looking at the various planets that we have here in our solar system. And we're fortunate in our solar system to have 3 roughly Earth-sized planets in the habitable zone, or on the border of the habitable zone with the case of Venus, that we can take as a data set to help us understand what makes an Earth-like planet Earth-like, and what makes the other planets not Earth-like. And now we're constantly learning more and more about Earth, and we have a number of missions to Mars, which are constantly probing Mars. But Venus is a mystery, and we really don't understand it. And to help us get a better understanding, long-duration missions are required. So therefore, by getting a better understanding of Venus, it helps us know what potential exoplanets we'd be interested in targeting in the future, so that we send probes one day to a planet that's an Earth and not a Venus, or maybe even more importantly, a planet that is going to be an Earth when we get there versus a planet that might evolve to be a Venus in the next 100 or 1,000 years. So I've got to thank a lot of people who contributed to this concept. There's a number of individuals at JPL, a number of individuals other places. This has been a wonderful topic to talk with people about, where lots of people have different ideas that they've been shared that have been looped into different aspects of this concept. So there's a number of individuals that I'd like to thank here, and I'd like to thank all of you for being here tonight. And with that, I'd like to open it up for questions.